So let's continue our discussion about something called the Gibbs free energy, which helps us answer the question, is a process or reaction spontaneous or not? Does it happen without outside intervention? That would be spontaneous. Or does it not happen? Well, this thing called the Gibbs free energy, or simply called free energy, is symbolized by the letter G, and when calculated, which we're going to show two ways in this video cast, if the number turns out to be negative, that means it's spontaneous in the forward direction. If it's at zero, it's at equilibrium. If it's positive, it means it's non-spontaneous or spontaneous in the reverse direction. One way to calculate G, or Gibbs free energy, is this equation. G equals H minus Ts, where H is the enthalpy in kilojoules, T is the Kelvin temperature, and entropy has to be converted into kilojoules from joules, and then you can calculate the Gibbs free energy. A second way you can calculate it is by using the Appendix C and the tabulated values of the Gibbs free energies and take the difference between the products and the reactants. We're going to do a sample problem of this first. So our sample problem will take and ask us to use data from Appendix C to calculate delta G for this reaction. So we'll take and find our Appendix C right here, and we'll have to look up the products, PCl3, subtract from that P4 and Cl2's Gibbs free energies. And so we'll do products minus reactants, where the little n stands for the coefficients in front of each one of these species. So you can look them up on your thermodynamic quantities sheet in the back of Appendix C. I'll just look up a couple of them with you, and I'll give you several of them as well. The first one is the product PCl3. PCl3, we'd multiply it by 4 because there's a 4 in the balanced chemical equation. You can see the 4 right here. And it's negative 296.6. And I look it up on here where there's phosphorus. And I look right down here, and it's PCl3, and it's negative 296.6. I subtract from that the reactants, and one of the reactants is phosphorus, P4 gaseous. P4 gaseous would also come from here underneath phosphorus. Whoops, right over here in this corner. And it's P4 phosphorus in the gaseous phase, so it's 24.4. The other piece that's in there is the chlorine gas right here. And so I look up underneath Cl here, I believe, chlorine up in this area, and you can see that Cl2 gas has a Gibbs free energy of 0. Just like the enthalpies are 0 when they're elemental conditions, so are Gibbs free energies. And as a matter of fact, a lot of things are similar between Gibbs free energies and enthalpies. If you're looking, here's a place in the textbook that talks about conventions used in establishing free energies. Solids and liquids are pure solids and pure liquids. Gases are at 1 atmosphere of pressure in standard conditions. Solutions are 1 molar concentration. And the Gibbs free energies for elements are 0 as long as its elements is in its standard state. So you might wonder about phosphorus up here, because you're like, phosphorus, P4, that's in its standard state. Yes, but it's in its gaseous phase. If it was in its solid phase, it would be 0 as well. Anyway, finding the difference between these two then, we end up with negative 1,102.8 kilojoules, and therefore, since it's negative, it tells us that this reaction is spontaneous in the forward direction. What would be the Gibbs free energy for the reverse of this reaction? Well, the reverse of the reaction, of course, would just turn around our calculations, and therefore it goes from negative to positive, and we'd say that that would be non-spontaneous. All right, let's take a look at this equation where delta G, or G, is related to temperature. And we'll look closer at this equation. This is the G equals H minus Ts equation. And this is where temperature starts to become more of a factor many times in the spontaneity, or how spontaneous a reaction is. This is sometimes known as the enthalpy term of the Gibbs free energy equation. And this is known as the entropy term, and it's many times written as H plus negative TS because you want to look at each one separately. How do the signs of H and S affect spontaneity? Well, let's take a little bit closer look at that on page 837 if you have the 13th edition. Otherwise, I'm going to zoom in on it on this photocopied page of it as well. So, if H is positive, if H is negative, I'm going to keep the equation up here as well. So we'll zoom in on this. There's the equation. If H is negative and S is positive, that means we've got a minus sign here, and we have a minus sign here with a positive value here. That means that TS is also negative, and therefore G is going to be negative, which means it's always spontaneous. It's going to be spontaneous at all temperatures. How about when H is endothermic and S is also negative, meaning that it is becoming more organized? That means the negative TS term, this parenthesized item, is positive, then therefore G will always be positive. And so you can see this is non-spontaneous at all temperatures. Doesn't matter what temperature you put it to, it's never going to be spontaneous. Notice the H and the S are opposite signs here for the times when it's always spontaneous or always non-spontaneous. The third possibility is when H is negative, it's exothermic, and S is also negative, meaning it's become more organized. That makes this parenthesed piece right here be positive. So we have a negative plus a positive value, meaning G could be positive or negative depending on temperature. This becomes spontaneous at low temperatures, making this term right here be a smaller numerical value than the negative numerical value of H. Then it would become spontaneous. It's non-spontaneous at high temperatures because this term right here becomes numerically superior to the negative H. Lastly, when H is positive and S is positive, now we have a positive value plus a parenthesed negative value. Well, the thing that would drive the reaction to be spontaneous then would be this one, because we'd want this to be larger than the H. And so it's spontaneous at high temperatures, making this parenthesed area right here be very large numerically. I mean, it would be large and negative as compared to the positive H right here. There are some example reactions for each one over here where each occurs to become spontaneous or non-spontaneous depending on the temperature. Anyway, this equation allows us to take temperature into effect and determine whether or not something will be spontaneous or not at various temperatures. So we just put this table down in here, and I'll do one other sample problem using this as well. Right down here, sample exercise 19.9, and we'll actually numerically look at this as well, rather than just look at it with saying it would be large and positive or large and negative. This one says, the Haber process for the production of ammonia involves the equilibria, and it gives the equation. And it says, assume that H and S for this reaction do not change with temperature. And then it has, predict the direction for delta G with increasing temperature. And then it says, calculate delta G at 25 degrees Celsius and at 25 degrees Celsius and at 500 degrees Celsius. Now, the first thing that we're going to need for this is we're going to need the delta H of this Haber process, which we calculated in an earlier video cast, and we'll need the delta S for this process, which we once again calculated in an earlier video cast. So I'll give those two to us here first. The enthalpy of this reaction is negative 92.38 kilojoules for the forward reaction, and the entropy for this reaction is negative 198 this is joules per Kelvin. And now, just knowing that both of these are negative, if we look back at our little chart, if we have a negative species and a negative species, both H and S are negative, it would be spontaneous at low temperatures and become non-spontaneous at high. So since we're calculating this at 25 degrees Celsius, which we'd probably call a low temperature, and then we're calculating it at a high temperature of 500 degrees Celsius, we'd probably say that it would go from spontaneous to non-spontaneous as we go. Let's do both calculations. Delta G is equal to H minus TS. And for 25 degrees Celsius, we'll take the H at negative 92.38 kilojoules minus T. Now we have to convert this to Kelvin, so that'll be 298 Kelvin plus 273 times, and we have to convert this from joules to kilojoules, which would be 3 to the left, so 1, 2, 3 would be negative 0.198 kilojoules to keep our kilojoules and kilojoules in the same units. So pushing this into the calculator, then at 25 degrees Celsius we end up with a negative 33.3 kilojoules for our delta G. At 500 degrees Celsius, we can go ahead and plug the same value in for H, 92.38 kilojoules. And now we're at 500 Kelvin, so that would be 773 Kelvin. I'm sorry, 500 degrees Celsius plus 273 to get it into Kelvin. And then we multiply that by the negative 0.198 kilojoules once again. And pushing this into our calculator, our delta G then at 500 degrees Celsius becomes 61 kilojoules. And so you can see that it goes from being spontaneous here at a low temperature to non-spontaneous here at a high temperature. That's the type of prediction that you should be able to make qualitatively and then quantitatively be able to put it into the same type of equation. Good luck with your thermodynamic problems.